Okay, let's look at an optimization problem given some constraints here. So we have x squared plus 3y squared plus 10 constrained to 8 minus x minus y equals 0. In Business Calc 1, we solve these by using this constraint to substitute into this objective function. They usually called it Q, the objective function. It's the function that you're trying to maximize or minimize. And we only, had single variable calculus, so we made the substitution. So for instance, let's look at this the old way. I can rewrite the constraint as solving for x or y. It doesn't matter. I'll just solve for x. So if I add x to the other side, we'd have 8 minus y, right, using this constraint function here. And then we take that and we substitute it in for x here. So instead of x squared, we have 8 minus y squared plus 3y squared plus 10. And we call this some function. We'll just say q. And in order to optimize max or min, we need a derivative equal to 0, right? So we'll do this derivative, and we're going to set that equal to 0. Since we have one variable, we're doing it with respect to y. Bring down the 2, 8 minus y. Chain rule it, so derivative of the inner function is a negative 1, plus 6y, and derivative of 10 is 0. Okay. So cleaning this up and solving for y, let's distribute this negative 2, right? So we'd have negative 16 plus 2y plus this 6y equals 0. 8y equals 16, and y is 2. Now that we have y, we could go back to our constraint, right? X equals 8 minus y, so x equals 8 minus 2, so x is 6. So most of these want to know the values of the variable x and y that would maximize or minimize the objective function. If it wanted to actually know what the minimum is, we need to substitute x and y. But now remember, the old way, we still need to verify that this is in fact a minimum. So we can either do the second derivative test or use our test point, right? If y is 2, choose a value to the left and the right, and substitute that into the derivative. So doing it this way, we have 0, and we try 3, I guess. If I plug in 0 for y, I'd have 2 times 8 times negative 1 plus 0. So remember, all we care is it negative or positive? That's a negative, which means it's decreasing. If I substitute 3, I'd have 2 times 8 minus 3 is 5 times negative 1 plus 6 times 3 is 18. So we'd get 18 minus 10 is a positive, increasing, which tells us then that is a min. Okay, so we are good. Or again, use second derivative test either way. And last, if it did in fact want what is the minimum, right, we still need to go back in and plug in our x and y. So we'd have 6 squared plus 3 times 2 squared plus 10, 36, plus 3 times 4 is 12, plus 10, and 4858 is our minimum value. Okay. The new way we use this, we introduce what this Greek symbol called a lambda. I forget how to spell A-M-D-A, I think. And it's called a Lagrange multiplier. Why would we do this if we have this old way? Because sometimes it's too much work the old way, or perhaps maybe even impossible. Okay. Here's how it works. First off, we call this constraint G, and we need to make sure it equals 0, which it does. Okay. If not, make it equal to 0, and then go about it. So what our first step is, let's separate this here. We create this new function capital F, and we're creating it with 3 variables. And what you do is you take your original max or min function, which we called q, whatever, or lowercase f. Take that function and add this g multiplied by lambda, though. Okay, so it's lambda g here, and then f or q or whatever there. Okay, f plus lambda g. Now, you might see this next step called L1, L2, L3. Doesn't really matter. I've seen different variables used for this or different approaches, but really the point is we need 3 partials. We need partial x. I probably wrote this way too close. Okay, and then we need partial y, and we need partial z or partial lambda. Now partial lambda, though, is going to just be g. We'll see that in a second, but this is going to just be the g function. Okay, so looking at capital F, take the derivative with respect to x. So here I get 2x. Here I get 0, right? There's no x. That's a constant, 0. Sometimes I like to distribute this and look at it this way, 8 lambda minus x lambda minus y lambda, but you don't have to. Once you get the hang of this, you'll see that if I'm doing derivative with respect to x, then that's just 1, right? Negative 1, but then I have this lambda, so negative lambda. And just as before, we set our partials equal to 0. Partial y, let's switch colors here. So now we have 0, 6y, 0, 0, 0, and then negative lambda. Okay. And we'll do a third color, blue again, I guess. To show that the partial with respect to lambda is 0, going through it, that's 0, 0, 0, right? Lambda is the only variable. We have 8, negative x, and negative y. But that was our original g function anyways, as long as it was set equal to 0. Okay. Now you have options here. Basically, the next step is we are focusing on getting x and y. Okay. The most common way to do this is to solve both of these for lambda, because then we could use substitution and set them equal to each other. For instance, if I add lambda to the other side, I would get lambda equals 2x, and I'd add lambda to the other side, I get lambda equals 6y. And if lambda is 2x and lambda is 6y, then that means 2x equals 6y, right? Because lambda, right, they're both lambda, so that I know they equal. Solve for either variable. I prefer x in this case just so I don't get a fraction, so x equals 3y. And if x equals 3y, then we could take that and plug it in here, right, our g function. So using both of those, we get 8 minus 3y minus y equals 0. So 8 minus 4y equals 0. Add 4y equals 8, y equals 2. And if y is 2, we could substitute one more time back into L3, right back into g, to get 8 minus x minus 2 equals 0. So 6 minus x equals 0, so x is 6. Y is 2, x is 6, 6, 2, just like we got in our old way, right? Y is 2, x is 6. So we're good. One thing to point out when doing these Lagrange multipliers, though, is that if it tells you it's a min, it tells you it's a max, it's assumed, like that part is already given. We don't need to verify like we used to. only based on the way that they built the questions.